Hi, in this module, we'll introduce fMRI, try to place it into its appropriate context, and discuss some of its usages. Finally, we'll go over some of the topics we'll cover in the rest of this class. Let's begin by taking a general overview of brain imaging. In recent years, there's been an explosive interest in using imaging techniques to explore the inner workings of the human brain. Brain imaging data has found applications in a wide variety of fields such as psychology, economics, political science, computer science, engineering, and statistics. You name it, really. In addition, it's been central to several emerging fields such as cognitive neurosciences, affective neurosciences, neuroeconomics, neuromarketing, and many more. In general, brain imaging can be separated into two major categories. We have structural brain imaging and functional brain imaging. Now, there exists a number of different modalities for performing each category. Structural brain imaging deals with the study of brain structure and the diagnosis of disease and injury. If you have a stroke or a traumatic brain injury or something like that, you might go into the doctor and get a brain scan, a structural brain scan, in order to see whether there's been any damage. Here, modalities include computed axial tomography or CAT scans, magnetic resonance imaging or MRI, and positron emission tomography or PET. Here's examples of a series of MRI scans taken over the same slice of the brain. Now, the interesting thing about this is even though MRI is a single modality for imaging the brain, we can tune it in different ways to highlight different tissue properties. And this is something we'll talk about later on. Functional brain imaging can be used to study both cognitive and affective processes. Here, modalities include positron emission tomography or PET again, functional magnetic resonance imaging or fMRI, which is the functional analog of MRI that we just discussed, EEG and MEG. Here's an example of some fMRI data. And here we have a bunch of images that are measured over time. That's where the function of functional MRI comes in. Now, we'll study changes in these images over time while the subject performs some set of experiments. Each functional imaging modality provides a different type of measurement of the brain. They also have their own pros and cons with regards to things like spatial resolution, which is the amount of spatial information in the image, temporal resolution, which is the precision of a measurement with respect to time, and invasiveness. MEG and EEG have higher temporal resolution than fMRI, but they do not provide as much spatial resolution. In contrast, fMRI is much faster than PET, and also provides better spatial resolution. PET injects radioactive tracers into the subject in order to measure brain activation, so it's somewhat invasive. fMRI, on the other hand, just uses large magnets, so it is considered non-invasive. Functional MRI provides a nice balance between these properties and has become the dominant functional imaging modality in the past decade. So functional magnetic resonance imaging is a non-invasive technique for studying brain activation, and during the course of an fMRI experiment, a series of brain images are acquired while the subject performs tasks. Now, changes in the measured signal between individual images are then used to make inferences regarding task-related activations in the brain. So, for example, let's consider a simple task where I do finger tapping for 20 seconds, and resting for 20 seconds. Finger tapping for 20 seconds, resting for 20 seconds, over and over again. Now, what I could do is I could look at changes in the measured signal between images when I was finger tapping and when I was resting to see whether or not there's areas of the brain where the activation is higher when I'm finger tapping versus when I'm resting. So what does fMRI data look like? Well, each image consists of roughly 100,000 different volume elements or voxels. These are cubic volumes that span the three-dimensional space of the brain. So let's consider that we have a brain and we split it up into 100,000 different boxes of equal size. These are the voxels. Each voxel corresponds to a spatial location in the brain and also has a number associated with it that represents its intensity. In this little cartoon image here, I put the number 39. We'll talk more about what this intensity means later on. So during the course of an experiment, several hundred such images are acquired, roughly one every 2 seconds or so. So basically the data looks as follows. We have 100,000 measurements taken at time 1, 100,000 measurements taken at time 2, etc., all the way up to time t. So basically we're going to have 100,000 measurements taken several hundred times with the temporal resolution of about 2 seconds. Now if we look at a single voxel of the brain, remember each voxel had an intensity associated with them. What we can do is we can extract that intensity value for that voxel across time, and then what we get is a time series such as the one below. Now this time series we can use to see whether or not the changes in intensity are correlated or related with the task that we performed, in this case finger tapping. Now, the most common approach towards fMRI uses something called the blood oxygenation level dependent, or BOLD contrast. Now, BOLD fMRI measures the ratio of oxygenated to deoxygenated hemoglobin in the blood. It's really important to note that BOLD fMRI does not measure neuronal activation directly, and that's really what we're interested in, neuronal activation. But instead, what BOLD fMRI measures is the metabolic demands of active neurons, so the oxygen consumption. So when neurons are active, they need to consume oxygen. This is something we can track using BOLD fMRI. So how does the fMRI signal change when you perform a task? Let's consider that we perform a very simple task such as clapping your hands. How does the fMRI signal change in response to that task? Well, the way it changes is described by something called the hemodynamic response function, or the HRF, and this represents changes in the fMRI signal triggered by neuronal activity. This is an example of the HRF. What happens is, when I clap my hands, the neurons spike and they need access to oxygen. Heavily oxygenated blood comes to that part of the brain and leads to a rise in signal. And this is what we see happening about 5 or 6 seconds after the fact. Now, this goes back to baseline, and after about 20-25 seconds, we're back to normal again. But as you can see, this is a very diffuse process. So just the simple task of clapping my hands led to changes in my BOLD signal that went on for almost 25 seconds. So this is something that's also going to kind of color the way we analyze data later on, and this is important to keep in mind. Now, it's pretty clear that fMRI data analysis is a big data problem. Each brain volume consists of roughly 100,000 different voxel measurements, and each experiment consists of hundreds of brain volumes. In addition, each experiment may be repeated for multiple subjects so that we can perform population inference. In sum, the total amount of data that needs to be analyzed is staggering, and that makes the problem very challenging from a statistical point of view, but it also makes it pretty fun. Other things that make the statistical analysis challenging is the fact that the signal of interest is relatively weak, and the data exhibits a complicated temporal and spatial noise structure. Here we see an example of the data processing pipeline for analyzing fMRI data, and we see that there's many steps involved, and we're going to use this to kind of walk through what we're going to be doing in this class. In the first week, we're going to be talking about data acquisition and reconstruction. So that's going to be the later modules that you'll watch this week. But in order to really understand data acquisition, we need to first know a little bit about MR physics, so we're going to start out by doing that. In the second week, we'll talk about experimental design and pre-processing. Now, fMRI data needs to be massaged a little bit before it's ready for statistical analysis, and that's what the pre-processing step is all about. Finally, the meat of the class is the data analysis portion. Here we'll look at a variety of different topics. So the first topic we'll look at is localizations. How do you determine which regions of the brain are active during a specific task? So for example, in our finger tapping task, can we look at the fMRI data and find which regions of the brain were active while we were finger tapping? The second topic is connectivity. How do you determine how different brain regions are connected with one another? Once we know that several brain regions are active during the task, we want to know how they communicate with each other and create brain networks that we can analyze. Finally, there's been a lot of interest recently in using a person's brain activation to predict their response or disease status. For example, can we use a person's fMRI data and predict how much pain they're feeling, or whether they're at risk for some disease such as early onset Alzheimer? Okay, that's the end of the first module. Next module will be all about MR physics, and I hope to see you there. Okay, bye.